It's your salvation, 'cause my heart brings you back. Hello. Are we ready to go? Can you see my
Yes.
desktop?
Yes.
Okay. All right. Okay. So today we're going to talk about the multi-level feedback queue. Now, next week we're going to start a new topic. So there's a reading assignment for the new topic on virtual memory. Okay. So it says read 2 chapters, but the first chapter is only a page and a half. It's really just kind of a little mini intro to the idea. So the first chapter is only 1.5 pages, and the other chapter is 9 pages. Okay, so that's the reading assignment for Monday, to start reading about virtual memory. Okay, and today we're going to talk about multi-level feedback queue, chapter 8, and we're going to look at the examples that are in the zip file window scheduling. And I've already downloaded the zip file to this machine. Okay, all right. So the multi-level feedback queue algorithm, remember the key idea is that we have 2 scheduling algorithms that seem to be good. Shortest job first gives us good turnaround time, and round robin gives us good response time. Okay, but both give you bad at the other one. Round robin gives you very bad turnaround times, and shortest job first gives you very bad response times. So there's this idea that both of them do something well, and neither one of them does 2 things good. Okay. So by blending them in a kind of clever way, you can get an algorithm that get the advantages of both and not the disadvantages of either. So multi-level feedback queue is a blending of shortest job first and round robin. Okay. Now the other thing that remember, so that's one real main idea to remember, that we want to blend shortest job first and round robin. The other thing is, we don't know what a short job is and we don't know what a long job is, because in an operating system like Windows, if I start up like Notepad, who knows how long Notepad's going to run? There is no sense that it could be a short or a long job. I could let it sit there running for days. Okay, so we don't have this notion of what's a short job and what's a long job. But we have another dichotomy. We have CPU bound and IO bound processes. IO bound processes are processes that just keep asking for one IO request after another IO request after another IO request. And CPU bound processes are processes that spend a long time just computing and don't do any IO. Almost every process is either CPU bound or IO bound, at least at any given time. Processes will be IO bound for a while. When they have enough data, they start computing. So then they are CPU bound while they compute with that data. Then when they run out of data, they become IO bound while they load more data. That's kind of a pattern that happens pretty often. So what people do is say the IO bound jobs are the short jobs, and the CPU bound jobs are the long jobs. Okay, so in our scheduler, we're going to sort of treat IO bound as short jobs and CPU bound as long jobs in the scheduling algorithm. Now it makes sense to think of IO jobs as short jobs, because here's what happens. A process asks for an IO request. Okay, so then it gets put in the block queue. From the point of view of the computer, it's in a block queue for a really long time. At some point, its IO is complete. It moves from the block queue to the ready queue. From the point of view of the operating system, that's almost like a new job arriving. You know, it's been so long since that job was running, it could almost think of it as a new job just arriving. Now, when that IO bound process gets down to CPU again, since it's IO bound, it's going to compute for a very short period of time and just block itself. Okay. At that point, it just goes into the block queue and it sits there for a really long time. When it gets out of the block queue, in a sense, the operating system can think of it almost as another new job. So the IO bound jobs really do look like short jobs. You know, they look like a sequence of short little jobs. Just do an IO request, you're done. Then when that IO request is completed, then the process gets started up again, but then it just does another IO request and it's done. Okay, so we'll take the point of view that the short jobs are the IO bound ones, and then the compute bound ones seem like long-term jobs. If you give one of them the CPU, it uses the CPU for as long as you give it to it, and then it'll end its time slice. Okay, because it doesn't ever ask for an IO operation, it'll end its time slice. It'll be taken off the CPU. When it gets the CPU back again by round robin, it'll just use up a time slice. Okay, so that makes it seem like a long-running job. So what people did was they figured out a way to combine short IO bound processes with compute bound long processes in this multi-level feedback queue scheduler. Okay, so what we do, let me switch to the whiteboard. I'm going to try to draw a picture. See if I can draw a picture that what we're going to do is we're going to have, well, here's a queue that represents people wait. Oh, well, actually, let me. Remember, probably the best way to think about this is like this: the states that a process can be in. Okay, so this is the running state. There's the run state. Okay, there's the block state. Okay, and here's the ready state. Okay, so here's the ready state. Okay, and you can go from blocked, you go from blocked to ready, you go from ready to run, you go from run to block, you go from run to blocked, but you can also go from run to ready if your time slice ends. Okay. The ready queue is where jobs wait in line to get put into the run state. Okay, so this is really a queue. Okay, so you can think of it as a list of jobs. So I'll draw it like here as a list of jobs. Okay, so here's a list of jobs. This is the ready queue. Okay, and we'll call this the front of the list. So you pick somebody from here and you put them in the ready. When a job is ready, you're picked from here and put into the run state. Okay, then somebody else goes to the front of the line. Okay, then after you've run for a while, maybe you blocked and then you get back into the ready. When you come into the ready queue, you go to the end of this list. Okay, so coming in here means you go to the end of the list. Coming out here means you come, I can kind of like, you go from here to here. So you come out of the front of the list to running, and you go from here to the back of the queue. Okay, so when you enter the ready queue, you enter at the back. When you leave, you leave from the front, and then you do round robin in here. Okay, so this would be the round robin scheduler. This would just say the ready queue is one list of jobs, and whoever manages to get to the front, they're the next one who gets to run. Okay, and then it doesn't matter if you block. Oh, same thing here. When you go from here and you enter, you'll enter this way. There's two ways to enter the ready queue, but they both put you at the back of it doesn't matter if you enter the ready queue this way or you enter the ready queue this way, you go to the back of the queue. And then you wait till you get to the front of the queue, then you get to be in the ready, then you get to run again. Okay. Okay. So this will be, okay. Now, what multi-level feedback queue does is actually put several queues here. I'll draw, say, just 3 of them. We'll see in a minute, there's actually a lot of them, but there's going to be several queues here. Okay, and this will be the highest priority queue. This will be a highest priority queue here, and this will be the lowest priority queue over here, okay? Okay. Now what you do now is the scheduler does round robin on this queue until it's empty. If this queue is empty, okay, this queue has his front here also. This queue has his front here also. You only go to this queue when this queue is empty. If there's nobody waiting in line here, then you go to this one and you do the same thing, round robin here, okay? And then if there's nobody in this line, then you go to this one, okay? So there's multi-level queues. Now remember the name is multi-level feedback queue. Here's the multi-level queues. We haven't said anything about the feedback yet, but here's the multi-level queues. Okay. We want the short jobs to have the highest priority. Okay, because we want to do shortest job first. So short jobs should have highest priority. The way you give remember now, short jobs are our block jobs. They're the jobs that came out of the block queue. They're IO jobs. Okay, so a short job is a job that's an IO job. Okay, so if you came into the ready queue through the block queue, then you should go to the high priority queue. And what we're going to do is we're going to change this one a little bit. If you came into the ready queue through here, that means you ran out your time quantum. If you ran out your time quantum, that's what we're thinking makes you a long running job. So you shouldn't go to the high priority queue. If you come in, you should go, whoops. Okay. If you enter the ready queue this way, you should be bumped down to the lower priority queue. So if you enter the ready queue this way, you will go into this queue, okay? In fact, what you'll do is you'll go into whichever queue is lower than the one you came out of. So for example, if you came out of this queue, if you went from this queue to running, then blocked, and then became, I'm sorry, if you went from this queue to running and then lost your time quantum, you'd go to the next lower queue. Then if you were in this queue and you went to running, and then you used up your time quantum, you'd actually go into the next lower queue. You actually go into the queue that's lower than the one you were in before. So when you go from this queue to running, if you end up not blocking and you end up using all your time quantum and you go this way, you return to the lower queue. On the other hand, if you're in this queue and you became running and you actually did an IO operation and you went blocked, then when you unblocked, you would get bumped up to here because now you seem to be an IO bound process. So if you leave the run state through a block state, then you end up getting back to ready. You go into the ready queue that's high priority. If you're in the run state and you go to the ready queue by ending your time quantum, you go to a lower priority queue than the one you were in, okay? That's the feedback part. The feedback part's determining which queue you go into depending on which queue you came out of and what you did, okay? If you got out of running by being blocked, when you unblock, you go into the high priority queue because you look like you're IO bound. If you went out of running by using up your time quantum, you look like you're someone who's CPU bound, so you go to the queue that's lower than the one you came out of. If you came out of this one because you did an IO operation, but now you're done with your IO, you'll move to that one. Then if you use up another time quantum, you'll go to this one. And we'll see there's actually a whole bunch of these queues. You can keep getting lower and lower and lower until you bottom out. Okay, right? So this is the feedback is the idea that you go, depending on what you did, depending on how you moved around in here, you go into which queue over here. the queue you go into depends on what you had happened over here. Okay. Oh, and if anybody has any questions, please feel free to interrupt me. Like I don't see you, and so oh, somebody told me there's a way for you to raise your hand. Does anybody see that? There's actually a thing. Yep, yeah, Sean, yeah. Yeah, how do you do that? I don't see that. That's not part of my interface.
There's a keyboard shortcut. You just press Alt and Y.
Oh, Y for Y. Yeah, okay, that made make sense. Alt Y. Okay. Okay, good. Yeah, yeah, and then unmute yourself and just ask a question. Yeah. So if you've got a question, just unmute yourself and ask. Okay. Does anybody have a question about this little, because I have to kind of cover this. I can't show you this picture and my desktop. I think unless somebody knows more about Zoom than I do, it seems I can only show you either this whiteboard or my desktop. Has anybody got a question about this picture? I can save the picture. I think when we go back to the whiteboard, it'll still be there. Okay, I'm going to go to the desktop because when I look at the okay, like here is a famous operating system that's called Solaris. Okay, oh, I'm sorry. We're in this folder here on the multi-level feedback queue. Okay, so this is the folder and there's some notes here that are about the multi-level feedback queue. So if you read these, a lot of what I'm saying is written up in these notes. I mean, it's in our textbook. There's one explanation of it in our textbook. I wrote my own little explanation of it here. Here are 3 more explanations. I stole them from 3 different famous operating systems books. So I scanned the pages that were about multi-level feedback queue from a few books, like this one's, and you can, if you want, you can read these. There's 3 famous operating systems book. Each one I got the section on the, let's see, where's
Professor, real
yeah.
quick. Some people are also saying that there's also a text chat. I don't know if you saw that.
I know that there is one. I can't find it. Where do I find? I couldn't find it in my interface.
For ours, at the bottom of the screen, there's like the invite participants. There's one that says chat, and that brings up the like text chat.
Wait a minute. Oh, it's under more for me, I think. No? Oh, no, wait. Is that it? There. That's it, right?
Um,
Do you see that? Is this the chat?
I don't see what you're looking at, but
Oh, you don't see. So, oh, it's right in front of my desktop, and you don't see it.
no.
See, I thought whatever was in my desktop was shared by you, but I guess not. Okay, but yeah, I think I have it up now.
Yeah,
Okay.
somebody asked, can you see this? So if you see that message,
What? So was that? Want to know if I could see the chat?
yeah.
Okay, I have it. Yeah, I have it up on a second. I have 2 monitors, so I have the chat up on a monitor now.
Yeah, sure. All right,
the-
cool. That's
the-
all I wanted to say.
Yeah, the trouble with the chat is it doesn't get my attention. It's awfully hard to focus on 2 monitors at once. So if you ask me a question by the chat, I probably won't see it. But if you raise your hand, that pops up a little green window on my desktop. So I think if you want to grab my attention, I think the raising your hand is better. The chat, I have to turn and look at a whole nother monitor to see the chat. So it might be a good way to ask a question, but you have to let me know, like with a raising hand thing. Okay. All right. So okay, so in the Windows scheduling folder, there's a folder on the multi-level feedback queue, and there's some notes in there, and then there's a couple of alternative description of it that I stole from a couple books. Okay, now here's an interesting one. This is the Solaris operating system. This was before Linux came out. This was the operating system for companies. This was the workhorse operating system for companies before Linux came out, and Linux killed this guy. Now, this guy made a lot of money for the Sun Corporation, and Linux, the Sun Corporation basically went out of business and got bought out by Oracle because they couldn't make money anymore out of Solaris. but it's still a famous example of an operating system. Okay, so here is their priority queues. Okay, so they had 60 priority queues. Okay, so they had 60 priority queues. And what they show you here is that each priority queue had a time quantum. So notice that this is the highest priority. So this is where you start. A short job is up here. So a very IO bound process would be up here in priority level 59. Okay, it only gets a 20 millisecond time slice. Well, because if you're a short job, the idea is you're probably going to be asking for IO real fast. 20 milliseconds, remember, is millions of CPU instructions. So that gives a process plenty of time to do another IO request. Okay. If, on the other hand, you're in this queue and you run out your 20 milliseconds, you actually don't do an IO, you drop down to priority 49. So you would drop down, they don't show all the priority, but you would drop down to priority 49. Okay, so you would start looking like a longer running process, so you'd move to a lower priority queue. On the other hand, if you're in this queue and you have your 20 millisecond time slice and you do an IO operation right away, you stay in this queue. When your IO operation is done, you'll just stay right in this queue. So the operating system will do round robin on this queue. Now, since everybody in this queue only gets 20 milliseconds, and notice this is one of the things we have to figure out is how do you ever get to these lower queues? If you just sit here and do round robin on this queue, why can't you just get stuck there forever and just never get to a job that's in a lower priority queue? That's called starvation. We call it starvation when you get stuck just handling things in one queue, and there's always somebody in the queue, there's always somebody in the queue, there's always somebody in the queue, and you never get to these other queues. That's called starvation. Let's reason why that's not likely to happen. Okay, these jobs are only given 20 milliseconds. Okay, one of two things is going to happen. They either use up their time slice, but then when they use up their time slice, they're put in another queue. They don't return to this guy. On the other hand, if they don't use up their time slice, it's because of what? Maybe I got an answer. If he didn't use up its time slice, it's because what?
It made an IO request.
Yeah, he made an IO request, but they take forever from the point of view of computer. So he's not going to come back to this queue for a long time. Okay, way more than, so suppose you have 10 processes in this queue. You go through them round robin, but every process either uses up his time quantum, so he ends up out of this queue, or he doesn't use up his time quantum and he does an IO operation, but they take a long time to process. So more than likely, you're going to just empty that queue out right away. If there's 10 people in that queue, probably within less than 200 milliseconds, you'll empty that queue out. And it'll be a long time before anybody returns to it because their IO operations have to complete. Okay, now you go to this queue. Almost the same thing happens. Okay, actually you would go from queue 59 to 58, but this picture didn't show 58. So you go to queue 58 and there might be a number of processes in it. Now they get a slightly longer time quantum, but the same kind of thing happens. If they finish their time quantum, they don't return to this queue, they go to a lower queue. If they don't finish their time quantum, actually if they don't finish their time quantum, they're an IO job, they don't come back to this queue either. They'll go to that queue. When their IO eventually completes, they'll go to this queue. Okay, so you'll be able to empty that queue pretty quickly. Then as you move down these queues, the same thing is going to happen. Suppose there's, like, I pick queue 30. Suppose there's 10 processes in queue 30. Okay, I pick one. He's either going to finish his time slice, but then he doesn't end up back in this queue either, or he's going to do an IO operation. As soon as he does an IO operation, he's blocked for a long time, plus he'll end up back in this queue here. So I can probably empty that queue out just if there's 10 queues in it, in 800 milliseconds, I'll probably empty that queue out. Okay, then I'll move to the next queue. Okay, so I probably won't end up seeing this kind of thing happen. Now, it is possible that as I'm emptying this queue, new processes keep arriving in this queue and arriving in this queue. But you'd need almost an unlimited, you'd need thousands of processes to keep entering this queue for that to happen. It's very unlikely you could have just processes just keep entering this queue and keep entering this queue, because there's just a limited number of processes running on the CPU. Okay, so you're not likely to get stuck in starvation. You're not likely to get stuck at a queue where every time you try to empty it, somebody comes at the end of the queue. And then, as you're taking care of them, somebody else comes in at the end of the queue. That's very unlikely to happen in this procedure. Okay. Now, suppose you're a really, really, really long running process. What's going to happen is you're just going to keep, really long running process means every time you get the CPU, you just use up your time quantum. You'll always move down, move down, move down, move down. What's interesting is, if you get down to this bottom time quantum, notice that you're given really long time quantums, 10 times the time quantum that you got at the beginning. Here's an interesting question. Why do they make the time quantums get longer as you go farther down? I think we mentioned it once in class 4. Does anybody remember? There's a good reason to make the time quantums get longer as the queues get lower priority. Yeah, somebody did it. Yeah, somebody said it in the less task switching. Yeah, if there's 10, if there's a bunch of processes in this time quantum, if they were 20 millisecond time quantums, no, these guys can't go lower. Once you're in this priority queue, you're bottomed out. You're a truly long running process. Suppose there's 20 processes in this queue, okay, and everybody else is blocked on I/O. Okay, so you have 20 processes down here. Everybody else is blocked on I/O. Okay, if these were 20 millisecond time slices, you would just be 20 milliseconds time switch, 20 milliseconds context switch, 20 milliseconds context switch, and the context switches would just be wasting CPU time. It's a lot better to do 200 milliseconds than a context switch, 200 milliseconds in a context switch. Then you've saved tons of context switching time. So since all these guys are CPU bound, why not use the CPU on them rather than using the CPU on its own scheduling algorithm? So as you go lower, the time quantums get longer. Now notice that down here, if you use up your time quantum, you've bottomed out already, so you just stay at that priority. Okay, so this is a classic example of the multi-level feedback queue algorithm, that the time quantums get longer as you get lower in priority. When you use up a time quantum, notice that when you use up a time quantum, you don't jump always down to the next lowest priority. Like if you're in priority 45, your time quantum is 40, but if you use it up, you drop 10 levels down to 35. Okay, if you're in 35 and you use up your 80 millisecond time quantum, you drop down to 25. And if you're at 25, you use up your 120 millisecond time slice, you drop down to 15. And then if you're at 15, you drop down to level 5. And if you're level 5, you drop down to 0. You might ask, how did they come up with all these numbers? My guess is they just ran lots of experiments. Solaris was an operating system used for decades. It was used probably from the 80s up through about 10 years ago. Probably over many years of using it, they tweaked these numbers to see what worked really well. Okay, so these numbers were tweaked to get things to work well for them. Okay. Now, what about Windows? Let's look at how Windows has the same kind of idea. Here's a similar picture for Windows. Okay. Now, unfortunately, this picture doesn't say anything about time quantums. I can't find the information on Windows time quantums. Okay. So this shows you the priority queues. Windows being Windows, everything's a mess. Okay. Windows has 31 priority queues, and it doesn't use half of them. If you notice, the priority queues there's two shadings. There's this lighter shading that's called dynamic levels 1 through 15. And then there's this darker shading called real-time levels 16 through 21. The real-time levels aren't used. At one time, Microsoft thought they could turn Windows into what's called a real-time operating system. That's a special kind of operating system. It's used in things like the navigation system of a jet airplane, something that has to always, or like the brakes in your car, something that has to respond in real time to events. So you can't somehow be stuck somewhere doing something and an event happens and you can't get to it. In a real-time operating system, the operating system guarantees that when events happen, they'll be handled right away. It's a very difficult thing to do. Microsoft at one time thought they could make Windows an operating system for everyone. They thought they could make Windows a real-time operating system, and it failed. So Windows is not a real-time operating system, and these levels are never used. Okay, so they just don't, they're part of the operating system, but you cannot put a process in these levels. So what Windows uses is levels 0 through 15. Okay, Windows has 15 priority levels. The lowest is 0, the highest is, well, the highest priority is 15, the lowest priority is 0. Okay, so they use higher number. If you compare these pictures, it's a little bit, see why people get sometimes confused by this stuff. Both pictures treat lower number as higher priority, but this picture puts the higher priority at the top. This picture puts the higher priority at the bottom. No, I'm sorry. No, I said it wrong. They use lower numbers for lower priority, higher numbers for higher priority. This one puts low priority at the top of the picture. This one puts lower priority at the bottom of the picture. So here, low priorities down here, high priorities up here. Here, low priorities up here, high priorities down here. But they both do use low numbers to mean low priority. Occasionally, low numbers mean low. Occasionally, people use low numbers to mean high priority. Occasionally, priority 0 will be the highest priority, and you'll occasionally see it used that way, but not in Windows and Solaris. Okay, now each one of these levels represents a cube. Okay. Now, here things get a little bit messy in Windows. A band of priorities gets a name. Okay, so the name high is given to the band of priorities from 15, 14, 13, 12, and 11. So from 11 to 15, that band is called high. Above normal is going from, 12 down to 8. Okay, from 12 down to 8 is called above normal. The normal priority band goes from 10 to 6. The below normal band goes from 8 to 4. Okay, and then there's this idle band, which I never quite understood. If you're idle, why do you need multiple levels if you're not doing anything? I actually don't know quite what they mean by an idle band with multiple priority levels. Okay, now if you call up Task Manager and you go to Details and you pick a process, you can set its priority. Now, this is not setting its priority level. This is setting its priority class. That's setting the class over here. Okay, so for example, this process, let's see, this process, it says its priority is above normal. That means it's in this band somewhere. I don't even really know whether it's 8 or 12. Windows won't tell you, but it's in that band. So when you in Windows, when you set a priority, you're setting the band of the process. So this Chrome process is in the above normal. Now let's see. What about another Chrome process? Now notice this one's normal. This one's normal. This one's normal. Above normal. That one's somehow special. This one Chrome process is going to be more special than the other Chrome processes. These are probably tabs. This one, well, actually, we can probably find out which one it is. Okay, this is the one that was There's the one that's above normal. Okay. Go look at its command line. So go up here. Oh, if you select columns, I can just turn on the priority column. So here, turn on the column that tells me the priorities, and also want to look at the command line. Ah, kind of obvious why he had higher priority. Okay, notice that here's the priority column. One of the chromes is above normal. One of the chromes is actually low. Another one's low. But you see why he's above? Can you see? Anybody see the hint why he's a higher priority?
Because he's using the GPU.
Yeah, he's the one who's responsible for talking to the GPU. All the other tabs talk to the GPU through that process. So he's kind of given a slightly higher priority because he seems to be more important. You know, he's the process that handles the communications with the GPU. So you can see that here. I'm not sure why these other ones are low priority. There doesn't seem to be. I don't see anything that makes them seem like they would be. You have to kind of keep scrolling over and over. You know, notice how long the command lines can be. Command lines are really useful tools for doing operating systems. Notice that these have huge long command lines. I don't know. I haven't seen anything yet that would indicate why this one would be low priority. No. Notice the command line just goes on and on and on. There's more and more. What are we looking at? Lots of command line arguments that were given to Chrome. Each Chrome process was started with a huge number of command line arguments, but I don't see anything that would give you a clue why some are low priority than others. Maybe because a tab hasn't been updated in a long time. Maybe it becomes a lower priority because it didn't get updated. Okay. All right. So Windows, every process is in one of these bands. Okay. Now, in Solaris, a process could start up here and work all the way down to here. If a process was truly a CPU-bound process, it would eventually move all the way down to priority 0. That's not the way it works in Windows. In Windows, you only move within your band. Okay, so a process that's in the normal band, he would start at 10, at priority level 10. Then if he used up his time quantum, he would move down to, let's see, now which way is which? He would start at, he would start at 6. You see, I'm getting mixed up in the directions of the two tables. A new process in this band would start at priority 6. If he used up his time quantum, he gets lowered to priority 7. If he uses up his time quantum again, he gets lowered to 8. If he uses up his time quantum again, he gets lowered to 9. If he uses up his time quantum again, he gets lowered to 10, and he stays there. If he uses up his time quantum, he stays in 10. Okay? But if he doesn't use up his time quantum, he gets boosted back up to here. Then he starts, then he's IO bound, and he'll sit there and if he doesn't use up his time quantum, he'll stay at that level here. Okay? So a process moves in he only cycles through those priorities. So every process only has 1, 2, 3, 4, 5 priorities that can cycle through. I have no idea why Windows did it this way. It's quite a bit different than the Solaris design. The Solaris design is a really classic multi-level feedback queue. This one's a multi-level feedback queue with these bands, and you only shuffle within that band. Now, what's quirky is that, for example, this priority queue, which is number 6, is got 3 bands overlapping it. So that means this priority queue has some processes from this band, some processes from this band, and some processes from this band. and they're all round robin in that queue the same, but they're not, well, not quite the same. So suppose you're in this queue, but you're from this band. Let's do this one. Suppose you're in this queue, this would be Q8, and you're from this this band here, okay? If you used up your time quantum, you drop down. And if this guy used up his time quantum, he dropped down. But if a guy from this band in this queue uses up his time quantum, he stays at that band. He stays at that queue, okay? So in this queue, there are processes from this band, processes from this band, and processes from this band. They're all round robined together, but they're not quite treated the same. When he uses up his time slice, he goes to there. If someone's from here and he uses up his time slice, he goes to here. But if somebody's from here and they use up his time slice, he stays in that queue, okay? So somehow Microsoft thought that was better than having this guy keep dropping down, okay? Notice that that could make it harder to empty a queue. Remember how we talked about how you're pretty sure you were going to empty a queue over here? Because when you would process all the jobs, all the processes in that queue, every one of them is either going to use up their time slice and drop to a lower queue, or do an IO operation and go to a higher queue. So you are pretty sure that you're going to empty out that queue. In Windows land, you don't really know for sure that you can empty out Q8, because Q8 can have somebody here who just sits there, he's running at, he's using up his time slice, but he's not dropping down. So he uses up his time slice and he gets put back in this queue. And if he's the only one in that queue, suppose you have just one process in this queue and he's just happily running on the CPU, he'll block everybody lower. Okay, so you really could have starvation in this case. So what Microsoft does, and I don't think Solaris needs to do this, but Microsoft needs to do this. Every once in a while, everybody is pushed from their low priority queue to their high priority queue. Okay, everybody gets pushed up to their highest priority queue. Okay, and that kind of starts the cycle of people dropping down again. Okay, so because Windows will stop a process right there and not let it go lower, it has to actually worry about this starvation problem, that a process can just sit there in that queue constantly saying, well, he'll constantly be scheduled because he's the only process in that queue. Maybe there's nobody higher priority yet, or nobody with a higher priority yet. So I'm sorry, nobody with a higher priority up here. So he would just kind of get stuck there. Okay. So Windows has a couple quirks to this process. One is that every once in a while, I don't even know what the time frame is, like maybe once a second, everyone gets boosted to their highest priority. Okay. And that's to try to stop starvation. Okay. And then another thing that they do is, see, this window here is what we call the front window. Now, right now, this window has is the front window. I could bring up this window as the front window. Okay, so there's three windows. This one's in front, now this one's in front, and now this one's in front. Okay, Microsoft gives the front window a boost, but not a priority boost. It gives it a time quantum boost. So this process here, since he's now in the front, he has a slightly longer time quantum than anybody else in his queue because he's the front process. So Microsoft has this idea, and that's to try to make the GUI more responsive. The GUI that's in the front gets slightly longer time slices so that it can get more things done quickly. Okay, so Microsoft has this notion of a front process priority. Well, it's not a priority boost. It doesn't change the process priority. It changes its time quantum. Okay, so remember this table here showed us the time quantums for the priority levels. They don't show the time quantums for these different priority levels. Like what is, if you're in this priority level, if you're down here, and well, if you're up here, you're supposed to be an IO bound process. So you would expect these to have very short time quantums. As you move down, you have longer time quantums, but at the same time, you can only move down so far. See, you can only move down to here. So my guess is the time quantums are adjusted not by what priority queue you're in, but possibly by how long you've been in that priority queue. Microsoft, as far as I know, doesn't provide much. Maybe I just haven't found it, but they only vaguely describe what happens to the time quantums. Unlike Solaris, which has this table, which shows you real clearly how time quantums work with priorities, which makes it real easy to reason about this. Microsoft's a little bit vaguer about how time quantums work. As a process is getting more and more CPU bound, it should get longer time quantums, but since it stops right there, it won't go to a lower priority than that. That would seem to limit how long its time quantum is. So I think it probably does get longer time quantums depending on how long it sits there. If it should ever use up a time quantum, then it goes back up to the top here and starts looking like a short running job. Now, here's another question. If you're down here and you issue an IO operation, you jump up to here. So you should get a short time quantum. If you're over here and you issue an IO operation, you jump to here. So you should also have a short time quantum. But these time quantums should be longer than these time quantums because these are the, so, I think because Microsoft uses bands, I think the relationship between priority and time quantum is way more complicated. My guess is the length of the time quantum depends on how long you've been in a priority queue, not which priority queue you're in. In Solaris, it's straightforward. The time quantum is determined by the priority queue. Lower priorities, longer time quantums. Higher priorities, very short time quantums. So it's real straightforward in Solaris. Okay. In Microsoft, they should be doing the same thing because that's the multi-level feedback queue algorithm, but they can't, since you're stuck in this band here, they would have to adjust the time quantums probably by how long you've been in each queue, not by just what level you're at. Because this is a high priority job here. He should be IO, I'm sorry. This is the highest priority here. That should be an IO bound process. Those should be IO bound processes. Those should also be IO bound processes, and those should also be IO bound processes. But they're in different queues. So they're in different queues. So in a sense, this is an IO bound process that gets served first, and this is an IO bound process that gets served later. So these IO bound processes get handled before these IO bound processes get handled before these IO bound processes get handled. So that might be an effective way to do it, is not treat, in Solaris's way of doing it, all IO bound processes are the same. They're all up here. So any IO bound process gets a 20 millisecond time slice. In Windows' point of view, you have high priority IO bound process, above normal priority IO bound process, and normal IO bound process. But in this queue here, he would be thought of as IO bound, but he wouldn't be. But they're in the same queue. See, they're in the priority level 10 queue. In this range, that's a process that is used up its time slice once, used up its time slice a second time, and is now down to here. So doesn't look IO bound. But this guy in the same queue, he should be IO bound because he's at the top here. So he's up here because he didn't use up his time slice. He issued an IO operation. Okay, so this process should have a longer time slice than this one. You would expect this one, even though they're in the same priority queue, this one should have a longer time slice than this one does. And like here's 3 different processes. This one has bottomed out in terms of being a long-running job. It used up its time slice here, dropped down to here. Used up its time slice here, dropped down to here. used up a time slice, drop down to here, used up a time slice, drop down to here. So it's pretty CPU bound. But at the same time, he's got somebody else in the same queue who's IO bound in this below normal. Okay? So this IO bound process at below normal has the same priority as this CPU bound process in above normal. I bet they don't have the same time quantum. I will bet that this has a longer time quantum than this one, but I don't know where that would be described in the. I don't even know if that's documented. Maybe it is documented if you read enough references, but I haven't seen it. Okay. So it's kind of a complicated algorithm, but at the same time, the idea behind it is pretty simple. Treat IO bound processes like short jobs. Give them a higher priority. Let the short jobs get out of the way first. Then after you've taken care of the short jobs, then you take care of the longer running jobs. Okay, so higher priority short jobs, lower priority long jobs. You expect these to have shorter time quantums and expect these to have longer time quantums, and they probably do. Okay, Windows decided to put them in bands. So, he bottoms out there. And, again, it maybe made sense to them. A process in this band really does get treated better than a process down here. Whereas in the Solaris system, there is no way to say, there's no way to say a process is more important than any other process. If you're IO bound, you end up at high priority. If you're CPU bound, you end up down here. So there's no way to say that one CPU bound process is more important than some other CPU bound process. Okay, because if you're CPU bound, you just keep going lower and lower and lower. Microsoft probably thought it was good to be able to say, well, we have a certain process that we think is more important than some other processes. So, so even if a process is IO bound over here, this IO bound process that's in this here, he isn't more important than a CPU bound process over here. Okay, so his IO bound process is treated about the same as his CPU bound process. That's actually kind of an interest. It's an interesting idea that an IO bound process here is somehow less important than a CPU bound process over here. This scheduler lets you do that. Solaris scheduler didn't. I don't know if anybody knows whether it's actually useful or not. Does it make Windows a better operating system? I've never seen anybody say one way or the other whether this is better than Solaris or not. Okay. Oh, and I don't know. I don't know how Linux works. Linux is also a multi-level feedback queue. I don't know if it's more Solaris-like or more Windows-like. Okay, I've actually never looked up the Linux scheduler. I probably should, but I've never really looked up into most of the textbooks talk about Windows and Solaris. You would think they would talk about Windows and Linux, but they tend to talk about Windows and Solaris. Main reasons, the operating system textbooks were all written 20 years ago. So there's lots of description of the Solaris algorithm because the books were written when Solaris was an important operating system. And most people haven't updated their operating systems textbooks, so there's not quite as much discussion of the Linux scheduler. So I'm sure you can find tons of descriptions. It's not in the textbooks, but there would be lots of pages that would describe them. Okay, all right. Now, again, remember, Windows lets you play around with this. If you go over here, you can set the priority. Oh, notice this one says real time. Don't put something up there in real time. It could lock up your computer. Real time is not, well, actually, I don't think it, real time is this band here. Okay, and like I said, these aren't used. Actually, I can't remember if you can actually put a process in this here or not. I don't want to try it. I think I've tried it in the past. I know that you can lock up your computer if you put the wrong process even in high priority. If you put some processes in high priority, remember, the way the scheduler works, if you're in high priority, you have precedence over all these other jobs. Okay, So notice that a normal job is not even overlapping with high priority. Okay, high priority overlaps a little bit with above normal, but it does not overlap with normal. Okay, so that means if there's somebody in here, as long as they're running and not blocked on IO, these guys don't get to run. And almost everybody's in the normal class. So if you want to mess up your computer, write an infinite for loop and put it in high priority. It'll lock out everything else. Everything from here down will get locked out. Task Manager, I believe itself runs in above normal. Let's see. So that so you're not likely to lock out Task Manager. Let's see, where's Task Manager? Oh, no, right now Task Manager is running at normal. That's not good. Okay, what would that mean? Suppose I took an infinite for loop and put him in the high priority class. And suppose I actually, now this machine has 12 cores. So I'd actually have to write 12 for loops, okay? Because I'd have to have one for loop to occupy each one of the 12 cores, okay? So suppose I wrote a program with 12 threads with 12 for loops and put that process up here, okay? Task Manager is running down here, okay? So the process up here would now be monopolizing all 12 cores, and what would happen? Yeah, like somebody said, you wouldn't be able to terminate the infinite loop because you couldn't call up Task Manager. If you clicked on the Task Manager tab, it would just be a little, you get a little spinning circle because it would not be processed. The scheduler would be staying in here, and that doesn't overlap with this. Now, if Task Manager was in above normal, there would be an overlap here, so you'd have a little bit of hope. I actually thought Task Manager ran it above normal. Now, if I want to, I can just go here and I could put Task Manager at above normal. Okay. Do you want? Notice it. Do you see the pop up? You know, it asks you, "Are you sure you want to do this?" Okay. Okay. Now my Task Manager is running at above normal, which is probably a little bit safer. You know, Task Manager is less likely to get locked out by a runaway process. I don't think I'd want to put Task Manager at high because the Task Manager has a pretty elaborate GUI. So the Task Manager is actually a fairly busy process. It's in its own sense because it's doing all this GUI stuff. If you made the Task Manager high priority, it might feel like it was safer, but you might notice that the Task Manager is gobbling up more CPU time than it deserves. Okay. So right now, this Task Manager is only using barely 1% of the CPU time, but like above normal is not a bad range. Now, see there's only a few processes at high. Right now, there's a couple at above normal, and the vast majority are at normal. Couple are at below normal, and then there's even a few at low, okay? The high priority ones are all operating system processes. These high priority ones, all of these processes are part of the operating system. Actually not, one of them is running as me. Yeah, so actually, I don't, one of them is a process I'm running, but all the others are processes, see, they don't have a username. They're part of the operating system. So all the other high priority processes are part of the operating system. And that also means that you probably can't change their, like, see, access denied. See, the operating system knows I'm a regular user, and it's not going to let me make a change like that. I'm not even sure an administrator can make a change like that, because that should be something that's guarded by the operating system itself, not even by an administrator. Okay, so I cannot set the priority of a process that I don't have access to. And let's see what else. Remember the base priority. No, notice here the column is called base priority, but if you right click here, it just says you're setting the base priority here. It should have said set base priority. And a base priority, oh, the base priority is this middle one in the range. Okay, so the base priorities are 4, 6, 8, 10, and 13. They're called high, above normal, normal, normal. But you're really, when you set the base priority, you're really setting the range you're in. So you actually start out at the low end, and as you use up CPU, as you use up a time quantum, you go up. Then if you use time quantum, you go up, up, up to lower priority. I'm sorry, the other way in this one. You start off over here, and as you use up a time quantum, you go to a lower priority. Then as you use a time quantum, you go to a lower priority. Then as you use a time quantum, you go to a lower priority, and then down here. Yeah, you start here and you move down. If you use up, if you do an IO operation, you jump back up to here. Okay, all right. Okay. Let me think. That's pretty much, I think, the whole. Windows has functions that let you, like you can do this in Task Manager. But remember, you can set the priority in Task Manager too. But you, in your homework assignment, you're seeing how to set affinity in functions. Well, anything you could do in the Task Manager, you can do using Windows functions too. So just like you can set affinity through a function, you can set the priority of a process through a function too. So one process could change the priority of another process if it has permission to. Notice that I didn't have permission to set some of the priorities. But so any function can set the priority of any process, can set the priority of any other process if it has permission to do that. So there are functions in the Windows operating system for manipulating priorities, just like there are functions for manipulating the affinity mass. Okay, we won't use those. In this homework assignment, like in the scheduler homework assignment, I could have let you schedule with priorities, but that would have just made things even the assignment's complicated enough just scheduling CPUs without having to worry about priorities. Okay, so but we could have had that assignment even have, say, some processes have higher priorities than other. If a high priority process arrived, it could have bumped a lower priority process off a CPU. That's something you could add to the scheduler, that processes have priorities and higher priority processes take precedence over lower priority processes. Windows, we would be able to do that with these functions. Okay. Here's a summary. This was somebody else wrote this, but this is a little summary that somebody wrote about the Windows scheduler. Okay, here, when a time quantum expires, the thread's priority is lowered, but never below the base. That's what we were just talking about. That, that's the multi-level feedback queue part of this. That you stay within this band. So as your priority is dropping, you don't drop below what your band is. Okay. Okay. Now, here's what's interesting. When a thread wakes, okay, when a thread wakes from a wait, that means when it did an IO operation, the priority is increased. Okay. So if you're here and you do an IO operate, if you use up your time quantum, you go down. If you do an IO operation, you go up. Now, I believe you go up to the top, but it might be you only go up one step. I actually don't know for sure in the Windows operating system that if you don't use up your time quantum, you move up. I think you go up to the top, but here he just says if you come out of a wait, then the priority is increased. And here he says higher increase if waiting for keyboard. So that would imply maybe what's true is if you come out of an IO operation, you go up, But if you come out of an IO operation away from your keyboard, you go up by more. So maybe you don't always go to the top. Okay. So maybe when you come out of an IO operation, you only go up 1 queue level. Maybe you don't go up to the top. The textbook describes it as when you do an IO operation, you go when you block on an IO operation, you become a short job. So you go to the highest priority. Okay. Here it implies that you don't necessarily go to the highest priority. That, for example, keyboard input makes you go higher up than others would. Okay. And then here's what I was saying, that priority is increased for foreground Windows processes. Now, this is the foreground Windows process, the window that's in the front, as opposed to this window over here. Now, he says that the priority is increased for foreground. My understanding is also the time quantum is also increased. So maybe both are increased. So maybe if you become the front window, you jump to the highest priority, but I know that you also get a longer time quantum. Okay. So it could be that you do both. He says here priority is increased for foreground processes. And my understanding was only the time quantum is increased, but maybe it's both. Okay. But notice that those are all interesting ideas. That when somebody clicks on a window, the idea is that since it's a GUI-based operating system, when somebody clicks on a window, the operating system should kind of jump to attention. It should be really ready to process that GUI window. But you don't want to click on a window and there be a 1 second lag or a 1.5 second lag. So it makes sense that you would boost the priority and also maybe boost the time quantum to give that process time to handle all its GUI events. So maybe it needs to repaint itself. Maybe it needs to repaint itself. Maybe it needs to process something. So it makes sense that since it's a GUI-based operating system, that when something switches from just background, what we call a background, changes from a background window to a foreground window, that it would get a bunch of different boosts. Maybe boost in priority and boost in time quantum. Okay. And this is another way of showing the same. This is a confusing way. This is a good example of how graphics matter. When you think about designing things, this table and this table say the same thing. This table says it in an incomprehensible way, and this table makes it real clear. So this is real good design. This came out of a book from Microsoft. Okay, this picture's out of one of their books. And you'll see this table in a lot of other books. See, normal, let's see, how do we, this normal here is this normal here. So this normal is bands 6, 7, 8, 9, 10. Okay, so normal is bands 6, 8, 10. Okay, I think that's how you read this. I mean, it's actually kind of it's very confusing because he's got normal up here and he's got normal over here, and you're not sure exactly quite what this means. Over here, notice there's only one normal. There's that normal band. Okay, okay. So this is a good. This came out of a well-known textbook on operating systems. This is a really lousy way to describe this information. Okay, so choosing a good way to explain information is always really important. Finding the right picture of describing something can really matter. This one's out of a textbook. This one's out of Microsoft's. This one's out of. I've shown you the book. There's this one book that describes the Microsoft operating system. They're called the Windows Internals books. Here's links to them. That picture should be in this. I thought it came out of here. Did I pass it already? I thought that picture came out of this chapter here. Huh. I'm not finding it now. I was looking at just before class. I was looking at it and I forgot which one of these books it was in. Maybe I just didn't go far enough. There it is. Okay. It's farther in than I thought. Okay. So like here would be where in this book they start describing these ideas. Okay. Okay. So priority levels. Okay. So they describe things kind of well in this book. If you're curious, you can read this. Okay. If you really like operating systems, or if you really want to be a world-class expert in Windows, you can read this. Okay, it's not easy reading. It's something that people spend. If this is something you like, think of this as something you can read over the next couple years. You could just keep coming back to this and reading it and reading it and learning more about it as you read it. Okay, yeah, it's a very famous book. You know, it really does describe a lot about Windows, but it's not a textbook like you're used to in college. It's not something you just read. You know, it's something you read and think about and just keep coming back to and coming back to. It's a pretty complicated. It's a fairly dense piece of reading. Okay, so if you want to see more detail, you can read any of this you want, but it's not required reading for this class. It's just something I wanted to put it there so you would know where to find it. So if you're interested in it, you can find it real quickly. It's right there. That's the free. These are links to the free parts of the book. The books are not cheap. They make a certain amount of them free. So I gave you links here to the part that's free. So for example, we're going to talk about virtual memory, and when we get to the stuff on virtual memory, there's this chapter on virtual memory. That's one of the free chapters, is the chapter on virtual memory. Let's see, where is it? There, memory management. Okay, so we'll dip into that a little bit when we get to the stuff on virtual memory. Okay, so we've run out of time, right? So, oh, one last thing. I'm trying to get the videos from these lectures up on YouTube or up on something. And it's not easy. Things are kind of all blocked up all over the place. So it took me, I had to wait till 2 in the morning to be able to create an account on YouTube. All during the day, it was so blocked up, it wouldn't even let me create an account. And then at 2 in the morning, I was able to create an account, but then I couldn't upload anything to it. Okay, so I'm trying to find where I could find a place to put the video for these lectures. Yeah, Nathan? Oh, I doubt it. I kind of doubt that I could put 1 GB, multiple 1 GB files up on that server. It's not a very robust server. Yeah, and then you'd have to download the videos. Oh, I don't know. Well, I don't know how to put up torrents. Blackboard, I was going to look to see if Blackboard had a site. I don't know if Blackboard, has anybody seen people put videos up on Blackboard? Have other professors put their videos on Blackboard? Okay, so I'll look at Blackboard. Okay, so I'll look to see if there's a site if I have a location on Blackboard where I can upload the videos. I assumed that YouTube would be the best place, and maybe just everybody else did too, and YouTube may have started metering stuff, so maybe it's not as open as it was even a couple weeks ago. So I'll look to see. Okay, I'll try. Yeah, when I find Brightspace. Okay, when I find a place to put the videos, I'll put a link to them on the website. Okay, so when I found a place to put the videos, I'll put a link to them. Hopefully in another day or so, or maybe later today, I can figure out where to put them. So, does anybody have any last question?
I have
Okay,
a question.
yeah,
So, when processes enter the system, the operating system doesn't know how much CPU time uh, it would need for each process. So, does it just figure that out by running them for a little bit and figuring out
no,
which
no,
queues to
it,
go in?
it assumes that everyone's an IO bound process at the beginning.
Okay, okay.
So it just puts them in the high priority queue and then lets them work their way to where they belong. If it's really a CPU bound process, it'll use up its times quantums and drop lower and lower and lower in priority. If it really is an IO bound process, it'll just keep doing IO requests and stay in the high priority. So the Windows just just assumes that they are IO bound and they initially start in the high priority queue. And then they feed back themselves to wherever they kind of belong. Okay? Because nobody knows if a job is really long running or short term. So you just assume they're IO bound, put them in the high priority queue, and then the algorithm will settle them into where they really do belong. Okay? Okay, so I'm going to end the class. Like before, if you have questions, you can send me emails. If you want to talk with me, you can ask me. We can arrange a Zoom meeting. So send me emails or yeah. And if you have questions about the homework, you should definitely be looking at that homework assignment. It's not a trivial homework assignment. So start looking at it right away. Give yourself time to think it over a little bit. Okay, I'm going to end the meeting now. Goodbye.